participants of the final seminar of the Quantum Karelia project, experts and members of our network from near and far. My name is Petri Raivo and I'm the president of Karelia University Applied Sciences. And I have a great pleasure and honor to open this seminar and welcome you all to 30 years old Karelia University Applied Sciences. And the name of the seminar is of course the Quantum Year is here. 30 years is a long period for the University of Applied Sciences, but quite short for the entire sphere of higher education system. Despite this, the rapid and successful implementation of the University of Applied Sciences system has been a major achievement of Finnish education policy. Universities of Applied Sciences located all over Finland have quickly established themselves. More than 500,000 highly educated professionals have already received their degrees from them. A considerable part of those who graduated from University of Applied Sciences find employment in their region of study. We have a national record here, which we are very proud in Karelia. In total, almost 17,000 highly educated professionals have already graduated from us, which is more than 70% have stayed to build the well-being and know-how of North Karelia, so they have stayed in this area. In fact, at least 1 in 10 employees in the region is educated by us. The nurses, social workers, physiotherapists, engineers, business, tourist and media professionals who graduated from Karelia have formed a significant part of their key expert in the working and business life in this area. In practice, almost 90% of the nurses and 80% of the engineers are made in Karelia in this region. Otherwise, the handprint of Universities of Applied Sciences in their own areas of operation is very strong. This is particularly evident in the research, development and innovation activities. In Karelia RDI activities, cooperation is carried out with more than 1,100 companies or third sector operators. What could be better for the regional influence of a higher education institution, besides education for experts, than to support the working and business life of the region in their product development work or to offer training that meets the new skills needs of the working life. But the fact that we do what the region needs right now is not enough alone. In all our activities, we must also aim for new perspectives, research subjects and dimensions. In their RDI work, universities have to look behind the twists and turns of everyday business life. Because companies don't have time to get there, and someone also had to try something new and something deviate from familiar paths to the very edge of the completely new and unknown. So that this area of unknown also becomes familiar and well-known, and that's how we get to the Kvantti Karelia and all that what it means. I was opening the first meeting of this project on February 10, 2021. At that time we were in a situation where the COVID pandemic, with all its difficulties, had already been among us for almost a year. And in my speech, I reminded not only of that, but also of the big changes that Finland has to face in the fundamental challenges created by the aging of the population, the transition in working life and climate change. And because of which we have to look for new technological solutions which we can adapt our lives and our mode to this new normal. All these phenomena, megatrends, are strongly related to the new wave of digitalization and the efficient use of data, various applications of artificial intelligence. Quantum computing and quantum computers are also very part of this new phenomenon. One of the strengths of higher education institutions is building communities. We have done this in the past, and for example, our precision technology or wood construction ecosystems offers companies in the field not only our own expertise, but also the entire network, both national and international, in which we are involved. And this we can also do with the case of quantum community. There is already a good example of higher education-based quantum ecosystems, for example, from Denmark. Why don't we use the results of this project and joint networks to create a similar joint here in Finland as well? An actor like Karelia University of Applied Sciences can be a bridge builder, a creator of connections, a forum that brings together a group of multidisciplinary experts and people who are enthusiastic about the issue to exchange ideas, network, and continue to think about and crystallize the issue. Something very important and essential can be born from it, and this Quanti Karelia is the most excellent tool for that. But of course, there is more than just the idea of community to gathering people sharing same kind of interests together. There are much more at stake. When we started Quanti Karelia, the COVID-19 pandemic was rampant. Now we have a total war in Europe, and we are heading towards a new kind of polarization where we have to choose sides in a situation where everything can be weaponized. Everything can be as a tool of weapon. And in this sense, quantum computing and everything related to issue are also to the greatest extent strategic tools. Indeed, something that can be used as a weapon, especially in wrong hands. Just under 2 years ago, I ended my opening speech with the words of Vladimir Putin, in which he stated, "The one who wins the artificial intelligence race will rule the world." Now, it seems even more sinister and ominous, and that is also why we here in the West, which defends democracy and pluralism, need forums like this. Ladies and gentlemen, all these talks in my mind, I wish you excellent seminar. Thank you that you are with us, and welcome to Karelia.
But Morten, Bache, or Bache, how you pronounce your name, you are a PhD and you are the director of quantum technologies research at Novo Nordisk, and you have been involved in the Danish roadmap for quantum computing and also now building the Danish strategy for quantum technologies in Denmark. So we are all very eager to hear your speech, and we are so sorry that we are not able to see you here with us in Joensuu, but it's that we have these connections that sometimes work. So please, Morten, the stage is yours.
Thank you, Christina and Olli, and thank you for inviting me. I hope you can hear me and see my slides and see me. Please confirm this.
Yes, Morten.
Okay, good. So this is it's a pleasure for me to speak to you today and talk about what we have done in Denmark in general to build a similar quantum ecosystem. And I am a scientific director of quantum technologies in the Natural and Technical Sciences Division at the Novo Nordisk Foundation. And to the right, I can show you a picture of our beautiful headquarters, and I hope someday I can invite you to come and speak to us and join in some of the quantum activities that we are planning here in Denmark. I'm going to talk a little bit about quantum in Denmark and how we in the Novo Nordisk Foundation got engaged in this presentation. But just let me show some work that we recently did together with RAND Europe in a report that I'm going to share with you later in this presentation. And these two graphs show the number of citations annually and the number of publications annually within quantum computers and simulators in general. So these are the search terms into the system dimensions, which has trawled a lot of policy papers, patents and stuff like that over the past 100 years. And when did the quantum computers and quantum simulators come about? That was around the 1980s, when Feynman famously claimed that you need a quantum computer to really solve quantum problems. And then there was a sort of an exponential growth in interest until the 90s. And then Shor and Grover came up with some great search algorithms that could solve some real problems on a quantum computer, even though we didn't have it yet. And then there was a really big quantum hype in the late 90s, early 2000s. And actually, at the end of this quantum hype, that's where I started my PhD and my postdoc working in quantum optics, where we tried to investigate how to use quantum correlations and quantum entanglement for something useful. And so there's a sort of a consolidation period here in the early 2000s where things are slowing down a little bit, because the hype is sort of, how do we really use these quantum properties for something useful? And that's where the nanotech area is really booming and starts to get, concrete. And then in the early 2010, I would say that the nanotech really picks up. It becomes very concrete. The hype is over, and you know what you can use nanotechnology for. And then in quantum, there was a really big research boost in the Majorana modes, and trying to figure out how to use them. So they were in Nature, Science, everywhere. And then in that period, there was an exponential growth, a little bit slower. And then there are some important things happen. So you got the D-Wave annealer, and you got the concrete IBM and Google quantum computers that can actually be bought for money, and not the Google one, but the IBM one and D-Wave, and you can actually use them for commercial purposes. And then you have what I would call quantum 2.0. You have functional quantum computers, and now suddenly we're entering into this area where things are picking up speed and momentum. And this is where countries like Finland and Denmark are now trying to build strong quantum ecosystems, where all these technologies are sort of consolidating into the quest of having quantum computers and using them for something. In Denmark, what happened was that in 2020, there was a report coming out from the consultancy company KPMG. KPMG themselves were very interested in quantum technologies, and they were asked by two independent public-private organizations, the industrial organization called Industriens Fond, and an IT organization called IT-branchen, and they wanted a report on quantum technology. Where is Denmark, and what can quantum technologies be used for? And they state in this report that it's important for Denmark to get the broader business ecosystem to function well, to create a solid foundation for quantum technology to be produced and or developed in Denmark. And so this report was very important for us in the foundation and all the other Danish stakeholders to use to push the politicians, governments, and so on to understand the importance of quantum technology. And what this report is also famous for is to show that University of Copenhagen is one of the leading quantum technology universities in the world. You see on the left. And on the right, very famously, the number of quantum technology master student graduated per capita is #1 in the world. So we really have a strong Danish quantum ecosystem on the educational level and on the research level in Denmark. And that convinced a lot of politicians that quantum was a real, not just a buzzword. And then at the same time, there was some grassroots efforts by researchers to form what is called the Danish quantum community. And I think this is quite parallel to what you are doing right now in Finland. It was 2019, 2020 that started. And they actually wrote what is a sort of a roadmap towards how Denmark can become strong in quantum technologies, which they published this year, the Danish Quantum Agenda. And they represent researchers to some extent, but it's mainly an industry organization representing trade organizations, other stakeholders, and big companies, big and small companies, in having a voice in quantum technology. And one of the things that they made in this Danish Quantum Agenda was to have a roadmap towards building a strong Danish quantum ecosystem, what is needed in the short term, near term, and long term in order for the Danish quantum ecosystem to become stronger and fulfill its potential. And then the government started picking up on all these things. And actually what really happened was a little bit of a confluence of a lot of actors. So the Danish, in Denmark, the US embassy in Copenhagen was very active on the quantum area. And at some point, Anthony Blinken was planned to come to Denmark in the early 2021. So they just changed the administration, as you know, in the States and survived the Capitol attack and all these things. And Anthony Blinken was appointed the Ministry of State. And he wanted to come to Denmark. And he had all sorts of important meetings. But what did he choose to do? He wanted to go to the Niels Bohr Institute at the University of Copenhagen and see the quantum technologies there. And this was organized by a couple of diplomats in the US embassy. And suddenly a lot of politicians and high-level Danish industry CEOs were left in a meeting room in another place in Copenhagen without meeting Anthony Blinken, because he chose to go to the University of Copenhagen to talk about quantum technologies. So they were A, little bit perplexed, B, a little bit annoyed that they didn't get to meet him, and C, they said, what is this quantum technology and why is he more interested in that in speaking to us? And that sort of interaction led to the Danish-US agreement on collaborating on quantum technologies that you see on the right here. So the foreign ministry went into the dialogue with the US partners on getting these agreements in place. And I believe Finland has done similar activities. So all this really led to the different ministries just picking up on this quantum technology. So the Ministry of Foreign Affairs published a report in 2021 on quantum technology opportunities in Denmark. Showing here on the left, they have a map on where are the big, strong quantum research institutions in Denmark. So there are two hotspots, I would say. So Copenhagen is full of quantum activities. And the other one is Aarhus, has a long tradition and especially in atomic quantum optics, quantum technologies. And then you have University of Southern Denmark in the middle, where they do more like nanotechnology. So they also started listing all the companies that are in Denmark getting involved in quantum, and in that way are now a sort of a hub towards people coming from abroad, from different stakeholders trying to get into Denmark and working with quantum technology through the organization called Invest in Denmark. Yes, and then they also had some list, top 10 reasons for choosing Denmark to work on quantum. And these kind of efforts were picked up in the government, and it meant that when we as a foundation and other stakeholders like the Danish quantum community, we could suddenly talk to 4 or 5 different ministries, so the trade, the foreign ministry, the main ministry of the president of Denmark, and we could also talk, of course, to the research and education ministry, and they all suddenly had quantum on the radar. And that meant that this year we started in the ecosystem in Denmark to do a mapping, and it was led by the Ministry of Education and Research. And that mapping led to some conclusions and highlights that you see here. I'm not just going to go through them, but this effort just led to Denmark officially now, maybe next month, will adopt a formal Danish national quantum agenda. What is sort of holding it up at the moment is that we just had an election and a 6-week negotiation on a new government. But all the people working on this are not elected. They are non-elected, non-political representatives of the government, but they just chose to wait on the new minister before they release formally this new agenda on the national stage. So all these efforts have just been slowly honing and focusing towards Denmark officially having agreements with important actors like the US, and officially having a national quantum agenda, meaning that we can actually have this as a strategic research area, and we can get strategic funding from the government to various activities. So research projects, small and large, research infrastructure investments, ecosystem development, national, international activities and relations and so on and so forth. So I would say in the past 3 years, things have gone from really grassroots to being quite spread out through the entire ecosystem, from the public to private, and from companies to small and large and medium, foreign, national, so on, picking up on this quantum technologies. And where do we come in? So I'm working in the Novo Nordisk Foundation. So I'm just briefly going to talk a little about who we are and what we do, and what our new strategy is, and what the quantum. I apologize for misspelling mission there. So the Novo Nordisk Foundation is actually a very old foundation. It's 100 years old around. And we own through a holding company that's called Novo Holdings. We own actually the companies that you might know: Novo Nordisk, world leader in insulin production, and one of the largest pharmaceutical companies in the world. And then also the biotech company Novozymes, and a lot of other companies that we own through investments that we have made through our holdings company. We are one of the largest foundations private foundations in the world. We are on the similar size as Bill and Melinda Gates Foundation and the Wellcome Trust. Last year, we awarded nearly 9 billion Danish kroner, which is close to 1.2 billion euros. And the investments that we have in holdings, they had a return of around 5 billion euros. And our total assets is close to 100 billion euros at the moment. Yes. And in the house that I just showed you on the first slide, we are both the Novo Nordisk Foundation, and we are also the Novo Holdings investment arm. So we have in the foundation focus on research and innovation grants to the public sector, not to the private, to the public sector. So we develop research centers and open competition grants. We have innovation grants. And on the early education side, we have activities in the house. And we also have a new foundation, which is called LIFE, which is supporting STEM education in a pre-K through 12. And then on the other hand, we have innovation, incubation, acceleration in a new foundation that we spun out a few years ago called the Bioinnovation Institute. And then when that early innovation stops, then we have the holdings arm take over and can make small investments and larger investments through seed and venture, and even from growth to up to principal investments. And in principal investments, we have multi-billion-dollar investments in large companies around the world. So we have a whole ecosystem chain here in the Novo Group. And what we are now aiming for is that we get quantum into more or less all of these bubbles here. So at the moment, we are mostly focusing on the research and centers and grants and then early innovation, but we're also getting it to the education and the acceleration part at the moment. And then we are talking to our holdings colleagues to get them to start investing in various parts of the quantum ecosystem. So the vision of the Novo Nordisk Foundation is to improve people's health and the sustainability of society and the planet. So it's a very bold and ambitious vision. We mainly support the funding in Denmark, but we also go internationally. And our main purpose is to support our companies, so that's Novo Nordisk and Novozymes, and to make sure that they have a good platform to perform their activities in Denmark. And in order to do that, we support research, so mainly in medical research and in diabetes and hospital activities that are related to that, but recently also to other scientific purposes, as in the last bullet point down there. And that's where the NATTech area comes in and the recent quantum activities as well. So our new strategy has two mission-driven areas, health and sustainability, where we have some clear goals on what we want to achieve in 2030. And then we have a base where they rest on, and that's what we call the life science ecosystem. And that's this place where the fundamental research takes place, the research infrastructures and the early innovation. And that's mainly where the team that I'm in is working and where the quantum activities are situated. So in the foundation, we have this quantum mission that we want to build on Danish and international strongholds within quantum. And we are on a mission to develop quantum computing to solve real problems in the life sciences. So we have a focus on generally on quantum technologies, but specifically on quantum computing and simulation, because we believe that these are the most critical ones to solve real problems, and a little bit less or so on sensing and not that much on encryption and communication. So we have been working since 2019 in the NATTech, where the division was formally founded, and I joined it in that year. And in that year, we had some early activities we made an early strategy where quantum was a key part of it. And we started an open competition program working on where we proposed a challenge where we could get around 8 million euros to 2 research centers if they could solve a big challenge of quantum simulators. And there we also started engaging in building the quantum ecosystem and the Danish quantum community. In 2020, we formally awarded these 2 challenge grants. So they are around 8 million euros each on quantum simulators and use them for solving life science problems. Then in 2021, we continued our ecosystem activities and made a big mapping on various quantum activities nationally and abroad. And we commissioned a report that I'm coming back to in a minute. And then we started planning a large quantum computing center. And that center was formally awarded this year. So it's called the NNF Quantum Computing Program. And it's 1.5 billion kroner to researchers at the University of Copenhagen. We also had some smaller activities this year that I'm coming back to. And then in the next years, with quantum is a big part of the new strategy. And that's where we will kick off this new quantum computing program, and also a new NATO test and acceleration site for quantum technologies have been awarded to Denmark, and is going to be located in University of Copenhagen. I'm going to come back to that in a little minute. So why are we in the Novo Nordisk Foundation engaging in quantum? Here I've shown you a list that you probably know about all the different areas where quantum technologies can have a potential. I would say that the quantum technologies that we are interested in are mostly on the left side of the slide. So it's the quantum chemistry related to biology, and it's all the machine learning, various parts of quantum machine learning that can be used to aid this. Then we also have some focus on quantum simulation on the top right, but not so much, as I said, on the communication and encryption part of it. So what we did last year was we commissioned a report from RAND Europe. RAND Europe is a research organization where you can commission a research project, and we told them to look into 3 questions. So one was, what are the current developments associated with the application of quantum computers to the life science applications? And what are the opportunities and challenges in this? And how are initiatives being adopted globally to strengthen the quantum ecosystem? And RAND Europe is, as I say, it is a research organization. So they do this as a research project. So the data collected for this project is very thorough and detailed. And you can now, it was released in October, and you can go into their website and download this report. And this report showed some key opportunities that are present in quantum technologies for the life sciences. And I just pause a little bit. So the foundation is a life science foundation at birth, because we came from the foundation actually of Novo Nordisk, the pharmaceutical company, and that's why we have a life science background. So therefore, we always have a focus on life sciences in our research projects and grants that we are awarding. So we asked, what are quantum computers used for now and in the future within life sciences? And they found some interesting application areas related to small molecule drug design and discovery, some quantum algorithms to generate large molecules, biological products and drugs, and personalized and precision medicine. That can be areas where the various researchers and companies can use quantum technologies in the future. They saw some challenges also related to this. The first one in particular is one that we saw ourselves, and we were very happy that they found the same, because it's one of the challenges that we solve in one of our big grants, namely that many life sciences use cases will require further developments in quantum development of quantum hardware and the development of specialized quantum algorithms. And there are challenges related to the wider ecosystem skills, and to the next one is about materials, so that the materials that are going to be needed for the future quantum computers are not necessarily found yet. So there's still need for investments there. And then there are some other challenges that I won't go through here. But basically, these first 4 ones are the ones that we are tackling in one of our some grants that I'm going to come back to in a moment. Then they also have found some key themes related to development of initiatives. So these themes are related to how you're going to build the ecosystem. So the national governments, they play a vital role in shaping the ecosystem, and that's also why in Denmark we have spent a lot of effort in not just working alone in the grassroots efforts, but really get the government involved. It's important to have national and international initiatives, and it's important to get companies engaged in what we call co-opetition. So it's cooperation and competition. So it's a friendly competition, let's say, between the different companies. You can imagine that a large pharmaceutical company will be very protective about the developments that they have in their R&D chain. But here the quantum technologies are so early that they really need to collaborate in order to gain some momentum in this area. So it's a very important message to carry out to the companies when you engage with them. And then there are some focus on startup companies. Having these adding dynamism and accelerating the pace of development in the life science area. Then they made some suggestions on key activities to grow the quantum life science ecosystem. And I put life in parentheses because I think a lot of them can be generalized to also the case that you mainly have in Finland, which is not necessarily the life science ecosystem. So it's about the diverse and skilled workforce, developing this. It's about inclusive and multi-stakeholder collaborations. It's about developing and participating in national and international quantum tech initiatives. It's about capturing the lessons learned and the different activities in order to learn from them. It's about incentivizing the private sector investment and nurturing the evolving startup and SME ecosystem. And I've seen that also in the Finnish. I have talked to some of your stakeholders in Finland, where they have some success stories about investments, but where it's really critical that there are the right venture capital and there's right actors involved in picking up the good ideas that are there. And then we talked a lot about this hype in quantum there, and then I think it's a good reason that there is a hype, but we just have to make people aware that you have to be patient and embrace a holistic, long-term and foresight-driven approach to development and adoption of quantum technologies. It's simply critical to communicate to people when you talk to them, the people that don't know much about quantum technologies, that this is the long game. This is a little bit like the fusion story we heard last night. I mean, it's really a 5, 10, 15-year investment that you have to do in order to accelerate the quantum technologies to fulfill the potential that they have. And some people don't really get this. But then they might just, then it's better, in my opinion, that they don't engage in quantum and do something else. In the report, there are lots of data, and the last half of the report is full of data that I helped them also curate. It's done in collaboration with Digital Sciences. As you can see on the right, Simon Porter was the one that I collaborated with. And this one shows simply that even on this shows the number of quantum computer and quantum simulator publications and citations by institution, and University of Copenhagen is in the top 10. Not normalized to country size or anything like that. So it really shows that Denmark has a strong research ecosystem. Here I just show you the challenge that we had, the quantum simulators. And it was awarded to 2 professors at the University of Copenhagen. One was on quantum algorithms and software, and one was on solid-state quantum simulators. And this picture shows the people that we gathered in our headquarters prior to launching the challenge. So we wanted all of them to join together, and we wanted them to find other actors to try and make consortia. And it actually turned out that this picture represents the first time the Danish quantum community was gathered in one room ever. They admitted that they had never really met all of them together, and this was in 2019, and it actually led to them forming the Danish quantum community. So it really shows the importance, and this was pre-COVID, of course. It was just half a year before COVID exploded. But it really shows the importance of gathering a lot of stakeholders often and mixing them together in order to get these grassroots efforts to flourish. One of the applications that we received that was not granted for this challenge was about using quantum computers and hybrid quantum computers, meaning quantum and classical computers, to solve quantum chemistry problems. And it didn't really fit in, and the committee liked it, but they couldn't really fund it. But then we picked it up, and then we gave funding for it through a standalone project earlier this year. We awarded it 40 million kroner, and they wanted to take classical quantum chemistry and to develop software and use cases for quantum computers. So they want to use NISQ type quantum computers, and we have the aim of the project is to we have made a partnership with IBM and gave them access to a quantum hub with broad access to half of the funding is used to get access to 8 nodes at this quantum hub. So it's the first IBM quantum hub in Scandinavia, and we engaged IBM also because they have a great team in Zurich working on both the hardware and the software, and they can give the researchers in Denmark a lot of knowledge and interaction. And the whole project is a consortium, and it's led by 3 researchers in quantum chemistry that you see on the right. And the idea is that they will run the hub, but they will also engage with industry and other universities and other international collaborators in order to develop these software programs and algorithms. And in particular, I want to notice that actually almost 60% of the compute time on the quantum computer is dedicated to industry. So industry can sign up for users as a node and engage with the researchers in order to get knowledge on quantum use of quantum computers and quantum algorithms. Just briefly on actually what they want to solve. So they are focusing on light harvesting protein complexes. So they are especially interested in transition states and not just ground states. So it's a little bit different research project than most other quantum computing projects today. And if you want to know more about this, please contact me or some of the researchers that I show you here. So as you probably know, NISQ type quantum computers are exciting because they are here now, but why do we want to go further than that and go towards fault-tolerant quantum computing? And that's because the noise in the qubits get a buildup of errors, and it limits the number of executions. But as you probably know, once you tell yourself, I want error correction on my qubits, then you make a big step towards the number of qubits that you need. So in a functioning quantum computer, a number of functioning logical qubits is, even with a few hundreds of them, you can solve really complex problems. But the problem with a fault-tolerant quantum computer is that the error correction code that you need to run doesn't scale really well. So we are facing tens of hundreds of thousands or even millions of qubits once you say, I want to have a fault-tolerant quantum computer. Why do we want this? Well, take a case like the Haber-Bosch process, which is currently run in big industrial size, as shown on the left, where you run it, you want to, for instance, make fertilizer, ammonia, which consumes 1% of the annual energy consumption on Earth. It's run at 500 degrees Celsius and 300 bar, but nature does it in roots of plants with a protein complex called the molybdenum iron protein complex. And in that, there is the iron molybdenum complex, which is actually synthesizing ammonia at ambient conditions, so room temperature and ambient pressure. Now, how can we learn from that? The Google team took some time investigating this, and on a superconducting quantum computer with a 1 microsecond cycle time, they say that if you want to simulate this protein enzymatic interaction, then it takes around 4 million qubits and 4 days of runtime. So these are the goals. And if we take another case, cytochrome P450, which is one of the major enzymes involved in drug metabolism, accounting for 75% of use, these cytochrome P450s, they have a group in the center of the protein complex that does the enzymatic activity. And again, Google sat down and looked at this and how you can actually do the calculations on this. And they again sat down and said, what kind of things can we solve on this and what is interesting? And ended up with, again, around 4.5 million physical qubits and a 73-hour runtime under certain criteria. And the challenge here is that the Clifford gates in the gate-based quantum computer versus the non-Clifford gates, and it's the non-Clifford gates that are really difficult to execute on a fault-tolerant quantum computer. And so that's why in the Novo Nordisk Foundation, we engaged with researchers at the Niels Bohr Institute to develop the quantum computing program with the vision to create a world-leading quantum ecosystem and with the mission to develop fault-tolerant quantum computing hardware and quantum algorithms that solve life science relevant chemical and biological problems. And the budget is really ambitious. It's 200 million euros, 1.5 billion krona over the first 7 years in phase 1. In this computing program, we have 3 areas that are all located under the same roof at the University of Copenhagen. So it's a full stack quantum computer approach. So it's about the quantum processor technologies. So building a quantum chip. It's about control and readout. So that's what goes on in the dilution refrigerator. And then it's about the software stack and the algorithms running it. So we have everything inside the project. They're located in Denmark, and the idea here is, as stated in the vision, that we build up a quantum ecosystem where we have all the technical expertise located in Denmark. The program is run by Professor Peter Krogstrup, who used to be leading the hardware efforts in Microsoft in the world. So he built up an entirely new lab in Denmark, developing quantum chips. But he believed that he could fulfill the mission of building a quantum computer better by going to academia. And the reason is that he feels that it's easier for the in an academic setting to collaborate. And in fact, already now the center has a lot of active satellites that are receiving funding. So apart from 2 other universities in Denmark, we also have University of Toronto in Canada. We have the Technical University of Delft in the Netherlands, and then we have 2 US institutions, MIT and Yale University. The program will focus on 3 different qubit technologies and not just one, which is also another thing that makes it unique. So it's apart from the classical or sort of traditional, I would say not classical, superconducting qubits, then there are 2 really strong areas in Denmark right now in quantum technology, that's spin and photonic qubits. And these are included as parallel tracks in the center in the phase 1 before a scalable platform is selected for phase 2. The center is set up in pillars that are where we have a lot of engineers hired to run the program. So instead of focusing on PhDs and postdoc, this is really an engineer-heavy research program. So around 20 engineers will be hired to build the quantum chip in what we call the quantum foundry, the two first pillars on the left. And then 5 to 10 engineers will be hired in the other hardware pillars. So the rest of the quantum processor technologies and the control and readout pillars. And then we have all the people working in the algorithms and applications. As I said, we had the focus here on fault-tolerant quantum computing hardware, and that means that we had to split the grant up into two. So a major part of the grant is given directly to University of Copenhagen as a research grant, but 400 million of the grant is actually given to establish a company which we call the Quantum Foundry. And that's because we want the quantum processor unit that is built as an interface between the two lower layers down here, the quantum processor technologies and the control and readout. To build that quantum chip, we want to keep that as a secret, as a trade secret, in where the technology rests in Denmark, because that enables us better to collaborate with other actors, public or private, academic or industry. And that was not possible on a university setting, so the company will actually be owned by the Novo Nordisk Foundation. So the whole program is sort of a hybrid between an academic institution and a private company owned by the foundation. So I'm not going to go through this. So just to show the timeline of what they want to do. So in the phase, right now we're building up the program. And in the phase 1, the different milestones are pointing towards selecting a scalable platform where you had a control over a logical qubit. And then in phase 2, to build a larger and larger quantum computer, scaling up the technologies, and then eventually have, at the end of phase 2, a quantum computer, fault-tolerant quantum computer that is big enough to solve real life science biochemical problems. And as a comparison below, I have shown you the timelines of the two other big initiatives that we have, the challenge grants and the hybrid quantum chemistry grants. So needless to say, this project, together with the two other projects, are some of the largest investments ever made in Denmark in the area in quantum, but also in NatTech in general. So the Novo Nordisk Foundation is really a key player in quantum technologies in Denmark. And I have to say that we don't do this in a vacuum. There's a lot of work that we do that is about managing expectations and aligning stakeholders. So we are constantly negotiating with universities, with small and large companies, with the government, with the various ministries, in order to ensure that the investments on this scale that we are making are in sync and in resonance and in synergy with all the other activities that are happening. I also want to mention that we are working in the ecosystem development in other ways. So, for instance, we recently held what we call the Nordic Quantum Life Science Roundtable. The purpose of this is to catalyze the quantum life science in the Nordics. And this is an initiative that was born last year in Sweden. It was the idea came from the Eva Carbonnier, which you see on the top of the steering group list on the left. She wanted to build up a quantum life science ecosystem in the Nordics, and she held the first roundtable last year in Stockholm in this sort of window where we were allowed to travel despite of COVID. And then the second year was then in Denmark, and next year actually we will have a similar roundtable in Finland, organized by the steering group member Sabrina Maniscalco from University of Helsinki. I was leading the local organizing efforts here in Denmark, and on the top right you see a group photo of us in the atrium of the So it's a very small roundtable. We were around 50 people engaging in panel debates and presentations and discussions about education, innovation, research, collaborations, all sorts of things. So these kind of activities are here. We are focusing on life science as a topic, and that allows us to broaden the sort of geographical scope a little bit out to the Nordics and not just Denmark or a few countries. So these kind of efforts are important in order to shape up the ecosystem. We don't really have a scope or an aim of the activities yet. We just have the steering group, and we just have the curiosity and the drive to see life sciences as a concrete application for quantum technologies and be a voice for making that happening across the Nordic countries. Yeah. So in Denmark, as I mentioned, we are really working across the ecosystem. So we're working on education, we're working on research, translation of research on the incubation acceleration side, and then we are actively trying to get seed investments to Denmark and getting the industry involved. We are, of course, in dialogue with our companies, Novo, Nordisk, and Novo, but also with a lot of other companies that could be interested in using quantum technologies. But it's very early days, so a lot of the companies are very reluctant to put too much effort into it. But I think this will change over the coming years. And then on the incubation acceleration side, we recently had the good news that NATO wants to put one of their incubation acceleration sites in Copenhagen, and that could now also be very interesting for you guys in Finland, since you are joining the NATO. And it's called the NATO Diana Center for Quantum Technologies. And Diana is a new defense innovation accelerator of the North Atlantic, and there comes the acronym Diana. It was approved last year by NATO, and it's part of their 2030 strategy, and where they put in a few billion euros into establishing some test centers, acceleration sites. I'm going to show some of them in the next slide, with the aim to foster transatlantic cooperation on critical technologies. And these critical technologies are the 9 ones that you see on the right. So you see you have AI, data, autonomy, biotech, hypersonic, space, materials, and energy, but also quantum. So quantum is one of 9. So Diana is not quantum, but Diana is all of these 9, including quantum. But the quantum center was awarded to Denmark early this year. And there will be test centers located around Denmark, and there will be an accelerator site at the Bioinnovation Institute, which is co-located with the new NNF quantum computing program that I just talked about. In connection with this, NATO has committed to make an innovation fund, which is a 1 billion VC funding for early stage startups and other deep tech funds. It's not entirely clear what they're going to use the funding for and which of these 9 priority technology areas, how the sort of the key distribution will be. But these things are being negotiated at the moment. So just to show you where these test and accelerator sites are located, so we have the Spore Institute on quantum, and then all the green ones are accelerator sites. There are 9 of them in different technologies, and the blue ones are test centers. And then there will be some test centers in North America and accelerators as well. These have not been decided yet. So you can see 2 things. There are a lot of activities on NATO on this side, and B, it's a lot of work to set this up. right now, because they decided this basically 1 year ago. And now there's a London office trying to implement all these test and accelerator sites and distribute the funding. So it's a massive parallel effort. It's almost a wartime like effort. NATO's idea about the technology is that it's dual use. It's application first, so civil use first and defense second. But exactly how it's defined and how much is defense and what is the defense, on what time scale do they see the defense coming in? It's not clear. But think of it a little bit like the DARPA programs in the US. And then you have to be a NATO country to be able to engage. So what we have done in the Novo Nordisk Foundation is that we were actually one of the authors of the bid to land the Quantum Technology Center in Denmark. And our proposal was to use the Bioinnovation Institute as an example of how a good accelerator should look like. So the BII was, as I mentioned before, was a foundation that we spun out a few years ago from the Nordisk Foundation. And to date, they have received 60 million euros of funding from external partners. So we have paid around 200 million euros to BII at the moment. They have created almost 70 startups already. It's a massive amount of startups that they are producing. And these startups are in the biotechnology area. But now with the Quantum Technology Center coming in from NATO, then they will also have quantum under their umbrella. So so this is just the accelerator part. And then there will be a number of test centers in Denmark, but I'm not going to talk much about them because I'm not involved in setting them up. But the accelerator part is me and a few other colleagues here in the foundation are involved in setting them up. And there will be an incubator program and an accelerator program. So the incubator will be for early stage spin outs and startups from the universities. And the accelerator program will be on a more mature scale. So these are just the standard BII operation models where they get some different programs, they get mentorships, and they have some team development and so on, and they get pitches, and they get we will attract VC. There will be a VC boot camp. There will be funders attracted and stuff like that. So there will be around 10 to 15 projects at a time at the Copenhagen site. Not all of them will be physically located from the NATO country they're coming from to Copenhagen, so some of it will be virtual. But you can still imagine that Copenhagen will be a really strong hotspot with this one on the innovation side, and then the quantum computing activities that we have just invested in. So I think 23 and 24 will be very interesting years for Copenhagen. All right, so that was just, I didn't even make a concluding slide. I'm sorry about this. Things ran a little bit faster. That's more or less what I wanted to say. I hope I didn't go too much over time. But I am now, if you have any questions, then please let me know. Thank you.
Thank you for the very interesting presentation and really inspiring presentation, Morten. And actually, I will have a few questions also for you, but I'm from the Finnish Technology Advisory Board, and for us in Finland, obviously, quantum technology is one of the most promising future technology areas. And well, Denmark is one of the forerunners, clearly, as we saw today, in quantum technology. And it was actually really interesting to learn how you have developed the blooming ecosystem, where the close collaboration between research institutions and industry, as well as the long tradition of public-private partnerships, are really the basis of developing the technology and the quantum technology solutions to solve complex problems. And actually, the ecosystem was the most interesting and inspiring element for me, because for me, the ecosystem is really the one that kind of enables creating solutions out of the quantum technology. And I have several questions also for that. But actually, my key takeout from this presentation is that the kind of the basis and background for the ecosystem is definitely the world-class research. And I was really impressed to learn that the University of Copenhagen is the only European university or the only European top research hub for the quantum computing in the worldwide. That was really, really impressive. And basically, the world-class research, the strong innovation system, and also the culture for the close collaboration and partnerships between different actors of the ecosystem are really the kind of the background and building blocks to create strong hub for this kind of a deep technology. And actually, it was also really interesting to see how Novo Nordisk Foundation and Novo Group are actually in the very key role in developing this kind of ecosystem. And you are really supporting the life science from the very beginning, from the education, starting from the education till the growth stages of the companies. So actually, my question is that how big impact you think that your foundation and actually the ecosystem that you have created, how big impact you have in Denmark, especially in the quantum technology field?
Yeah, it's very big in the sense that we are almost acting like a government foundation or a government. So we see ourselves a little bit like that and try to behave responsibly in that sense. So we have sort of created this trust between the partners, so that when we engage in something, we of course have our own perspective, but we also try to see everyone else's perspective as well. So we don't just come in with our opinion and then leave. We always try to set up meetings, and when we're in the meetings, we know we are the foundation, but we also know that we in principle also represent some of the other actors that are not there at the meeting maybe, and speak their case. And this has been the approach from the beginning, because we could see that we had the ambition of putting 7 billion euros into quantum, and that nobody else could do it. And that's where we started saying, okay, but then if we are doing it, then we should let everyone know that we are doing it. So we told the government, we told the universities, and we told companies that we were doing this in order to make sure that they knew that we were coming up with these large investments. And what is a little bit embarrassing, it's natural, but it's a little bit embarrassing still, is that until 2019, the Novo Nordisk Foundation didn't do anything at all in quantum. And as I showed on the point about the first slide I had was exactly to show that in the early 90s, quantum technologies really picked up from the quantum technologies settled in and so on. And then there was quantum 2.0 at the end. And in all that phase, the Novo Nordisk Foundation is completely absent in Denmark. And it's other founders that are giving the funding and making sure that the ecosystem grows, and that the strong research base that we have now is entirely I can say that with 100% confidence, entirely due to other people's funding, right? So we are not like Wallenberg with very long tradition on the area. We are really newcomers, but we come in with a lot of funding. So that, how do you do this? That has been a challenge to keep the good relationships, also with the other foundations, because it's only in the past 10 years that the Novo Nordisk Foundation has exploded in value. So we also have to be a little bit humble in that context. So we are really like the VC funder who comes in at a late stage and provides a lot of funding to a promising company. That doesn't mean that they can. So they're just a different actor, and that's how we see ourselves. And we really early on engaged in the ambition on creating the ecosystem, because the picture I showed where we gathered the Danish quantum community in our foundation, and it was in 2019, and they just told us, wow, this is the first time ever we are in the same place at the same time, and actually maybe we should do this more often. And then they created formally the Danish quantum community. And then we thought, oh, this is very inspiring. We can actually gather people and make them, make them feel that they are together and feel that they have some kind of common purpose. And then we try to, in various other ways, to do this in other connections. But that was sort of the growth and the inspiration. So it's just to say, I hope it's clear that we don't just develop grants and hand out funding. We really just try to be a voice across and be a representative for many people. But at the same time, we also let, when the Danish quantum community goes out and speaks, we are now a member of the Danish quantum community, but when they speak for themselves, let's say, and they have their own voice. So you have to know when to say something. You also have to know when other people come in. And right now there is a really positive sort of synergy between various actors. So various industrial organizations are having quantum initiatives and quantum seminars and stuff like that. And this is really interesting to see that they are sort of on their own trying to make something work.
Actually, you revealed the secret that you have, because I was planning to ask, from the presentation, I'm really able to see that you have really systematic approach, how to develop step by step the things to the future. But actually, something that was there in between the lines was that you actually have really specific culture. And I was planning to ask that what is the secret behind that? But actually, I noticed that actually you have really strong role as a facilitator and maybe an orchestrator of this community, this ecosystem. And I think that's something unique that you have. And because it's not just a systematic process, but you also need to kind of create the glue between these different actors. Was it something that you made? Did you make any kind of a strategic decision that, okay, facilitation is something that we will really do to make this happen? Or was it something that you just somehow noticed that this is actually something that works? Is it a strategy?
Yes. Actually, so when we made this first symposium in 2019, it was actually an idea we had, because we made this, the challenge program that we have is thematic. So every year there's a new theme. The next year was about nanotechnology, and the year after that was about energy, materials, and so the theme changes. But the first year was quantum, and then we said, if we want a successful open competition call, it's a little bit like the ERC synergy program in size and scope. If we want a good consortium, we wanted 10 consortia to apply, maybe. We need to gather them all here. And so we had this event, and then they were here, and then we felt that there was a really positive energy in them coming here, and then we decided to do that often and in other areas as well. And the key thing here is to create the sort of desire and trust of people coming here, that they come and they know that they get something out of it, and that so you have to create this atmosphere where they come with a positive mindset of meeting new disciplines, new research, and so and that as a foundation takes a while to build up this trust, because they might always ask, but why is the foundation interested in this, and how are they doing this? And you also have to see a little bit who's the best one to do it. In your case, I mean, it's about we turned out to be a good place to do it, and it's just something that you feel when people come, and when people drop everything that they have to come, right? It's about getting that kind of atmosphere going, and that is the trust that I think that we have built up slowly over the past 3 years. Because as I said, it was not at all obvious why we should go in as a new foundation on the quantum area and just be the main player. There's no tradition. There is no timeline showing why we should do it. We just wanted to do it, and we had a lot of money, but that could also be seen as a little bit of, offensive of the others. They had done all the hard work in the past 20 years, and then suddenly this new foundation comes in with a lot of funding and a lot of money, and then it's like a little bit like the Arab countries with the oil money. And yes, it's fun to have the money, but what do they really mean by it, and what? So we have to build up that trust with meeting with them, talking to them, make sure that they trusted us, and that has, and it's also why they wanted to hire someone like me who comes from the community, because it's easier for someone like me to speak to the researchers, because I come from where they are. So that's also part of the strategy, I would say. But it is a tricky thing, and I think you have to go case by case and country by country to see what works. But I think it's important to have some common place where you go to, like an event or an annual thing. A biannual would be even better, where you really say, this is where we go to discuss quantum technologies, to figure out where we're going, to gather the whole country and invite some other stakeholders as well, and get the companies involved, and get also the regions and the municipalities and whatever you want to get involved in order to lift some kind of agenda.
Thank you. And this is actually the key takeout for me. And I guess that also many other people in this event saw the same kind of, I think that's even a missing piece that many countries have, that they may have the knowledge and the researchers, they have the industries, they may even have the money, but if you don't have someone who is able to build the trust and facilitate the community, I think there's no way to succeed, or at least it's not that easy. But thank you. This was really, really inspiring.
And I think that actually you said that we were further ahead than Finland. I mean, I'm not sure I agree. I think in Finland, you this effort here that we are closing down today, I suppose, it was started way before the Danish initiatives. This is very recent, all of it. It's like the past 2.5 years. And then you already have a company building quantum computers in Finland. We don't even have that. We have visions and dreams. This is not the same, right? So actually, when we present our visions and our ideas, people say, yeah, but Sweden, they have the Wallenberg quantum. So it works already. And in Finland, they have already a functioning quantum computer, and they have a successful company. And so you are already 3, 4, 5 years behind. And how do you pick up on that? So we just hope that we will one day catch up with what you're doing in Finland and Sweden, I have to admit. But we have a very strong starting point in a good research ecosystem. They just never really built a quantum computer yet. Yeah. They are getting there, but we are, in that sense, we are behind. And then we have been very lucky about the ecosystem in the past 2 or 3 years, in the sense that there's a lot of grassroots work by researchers and companies. And then we had this luck of Anthony Blinken just wanting to go to the Niels Bohr Institute. That was a really big game changer. Everybody started talking about quantum everywhere. And that was a stroke of genius. Actually, the guy that worked at the American embassy who orchestrated this, we now hired him to do US DK relations in various areas. So he's now based in the US, but he was really, really instrumental in making this happen. And that was sort of the where you go to the other side, the point of no return, where the momentum was suddenly very large.
Just to conclude our discussion, I think, the Nordic countries, Denmark, especially Denmark, Sweden, Finland, we all have really strong bases in quantum technology. And I think that's also a good basis for collaboration. And that's something that we should look for.
Absolutely.
Thank you both, and thank you, Morten. That was really, really impressive what you were talking about, and I think we all got some very vital information. Then, Anita, don't go away. I have something for you too. So, so thank you so much, and of course our greetings to Denmark and lots of success to all your projects. Thank you. And Anita, you were so fast that I didn't have the opportunity to present you, and Anita, you are one of the persons and professionals that has been maybe the greatest opportunity for me to cooperate with, and that was really a good time when we did work together. And you are the Secretary General of the Finnish Technology Advisory Board and quite an influential person in tech in Finland. So I have a question for you. Now that you have heard Morten's speech, so what is Finland replying to Denmark? What is your what kind of greetings are you sending to Denmark? What are we doing right in Finland? Okay, Anita's voice just
sorry, that was my fault. Now I guess that you can hear me. Well, like Morten said, the strongest thing that we have is the implementation. We are really good in tech and we are really good in implementation. And I think something that we could learn from Denmark is how to create a community. Because if we are able to create this kind of a community and ecosystem like Denmark has done, and then we have the strong ability to implement the top research that we have in Finland, I think then we will be the world class. Really, or we are already, but we will also create value out of that.
Absolutely. How was quantum computing presented in the latest report, from high-level report that you were involved with?
Excuse me?
How was quantum computing included in the latest report that you were the secretary for the high-level report?
Do you mean the technology advisory board report?
Yes.
Well, quantum technology is one of the areas that we are really recommending that Finland should focus on. So that was one of the areas, because anyway, we are a small country like Denmark. So we are not able to be at the top in all research areas. So we really need to focus on few research areas that are really promising ones. And of course, quantum computing is one of those. So it's a really, really strong part of that. And we are really hoping that our report is read by many people, and also the quantum technology will get the kind of impact, or will get the impact that we are hoping that it will get.
Thank you so much, Anita. And please send a report to Morten if you have it in English, so maybe he can get some ideas. And yes, and now, well, yes, there are lots of opportunities in Finland, and now we are going to one of those great opportunities. The chief scientist and co-founder, PhD Mikko Möttönen. Everybody knows Mikko here in Finland. He is very famous. He's kind of our quantum rock star, many times awarded, and founder of IQM Finland Oy, which is our hope for the future in quantum. Welcome, Mikko. It's good to have you here. Some applause for me.
Thank you, Christina, and thank you, Olli, for inviting me. It's been a pleasure to visit Joensuu again. I was here last summer, and now I'm enjoying the winter. And what I wanna, thanks Morten for the great presentation of Denmark and acknowledging also the Finnish strengths. Very often I say that Finland actually has the largest quantum industry per capita in the world, and I think that still is the case. And I want to give you a little taste of that here during my talk. But before that, I really want to. Okay. I want to ask you the question that why are you actually listening to this talk? You know, is it just that you were invited and you're just here because of that? No. The reason why I'm here and the reason why you are listening to this talk, I hope, is this. We don't so much, we appreciate the history, but what we are really doing is to be looking into the future. And if we want the future to look like this, a green, sustainable, high-tech future where people can live their lives happily. This is where we really need quantum. We need that because we can't just use the technologies we have now in a sustainable way to live like this. So that is one of the reasons why we spun out IQM. IQM is a quantum computer company. We build quantum computers. We have now more than 200 people employed. About half of them have PhDs in quantum or in some other fields, supporting fields. We have more than 40 different nationalities. So we're really an international company. And so far we have actually 4 companies, not only one, but we have also companies in Germany, in Spain, and in Paris, or in France. And we have been able to get about 180 million of equity investments, some, I think 50-70 million of grants. And we are on a way to build a big company in Europe or starting from Europe to lead the quantum revolution. Here is a slide of our sort of history. We started in February 2018 with the sort of just a trial to spin off the company. We had like 2 people back then, just trying. Then about 3.5 years ago, we got our seed funding round closed, and we hired our first person a few months before that. Then 3.5 years ago, we hired about 20 people to begin with. And as you can see from this sort of history, we have been quite active on doing not only finance, not only funding rounds, but also building the technology and spreading out to different countries in Europe. And what the mission of the company is to be a well-being company in building quantum computers for the well-being of humankind. And we're doing it right now. We're right now building these quantum computers and delivering them to customers. We call this a foundation era. So already now, research centers, universities, and national labs, they want to use these quantum computers to educate future makers. And also perhaps companies want to test how these quantum computers can perform so that they can, in the future, use them for something good. For the companies especially, it is important to get commercial quantum advantage. And that is going to be the next stage of this development. So we are doing everything we can to make special purpose quantum computers that can bring quantum advantage to companies. Because we think this way, these quantum computers can bring also benefits to the society. And of course, when we get commercial quantum advantage, we get more funding to develop quantum computers further to the disruption phase, where we have so-called general purpose quantum computers. That is when we have quantum error correction and we can scale up just the number of qubits without worrying about the gate fidelities that I will come to later in this talk. So this is the future. We are now at the foundation era. Soon we will enter the advantage era and later the disruption. I have this nice video about IQM quantum computers. I hope it will run. I'm not sure whether you guys can hear the sound in Teams, but at least I hope you can see what's going on. Aha. Okay, this is the typical issue with the videos. Let me try. All right. Sorry about that. I think now it's be okay. Yeah, so there in the video you saw a little bit how the quantum computers look like, and perhaps a glimpse or a sort of an intuition into the world of the future when we are solving some of the hardest problems that there is. At IQM we have a great marketing team, of course, as well, and thanks to them we have been featured in many of the prime media in the world. We are also happy that we were invited to the Independence Day reception by the president last week, Tuesday. So that was a great moment for us. We have invested quite heavily on the infrastructure. This is, I don't know, maybe it's the biggest cost we have in a company. And one of those infrastructures is our chip foundry. So we have actually built a foundry in Espoo, in Finland, where we can produce quantum chips. This is pretty amazing. Here you have a photo, a glimpse into the actual clean room where these chips are made. So with this foundry and the later sort of extensions of this foundry, we think we can produce the best quantum chips in the world, especially for the quantum advanced phase. We are selling these full systems, working quantum computers, and our first customer was a VTT, or is still VTT, in Finland. That was a great decision by the government to acquire quantum computers in Finland. And we have already delivered the first 5-qubit quantum computer to VTT, and early next year we will finish the delivery of the 20-qubit quantum computer. And then about a year from that, we are aiming to finish the delivery of 50-qubit quantum computer. So that is now our prime target to be building this, but of course it doesn't end there. We are going for hundreds and hundreds of qubits, and we think perhaps a few hundred qubits with very high gauge fidelities, so very accurate qubits, can bring early quantum advantage. That's our aim. We have also a second customer that we have announced. It's in Germany, LRZ, an HPC center, and we are also going to deliver their 20-qubit quantum computer. We already have delivered their first machine, but the 20-qubit quantum computer will be the target for this delivery. As you can see in the map, many governments are investing heavily in quantum technology, and our aim is not to only deliver to Finland and Germany, but all over the world. So we're discussing with many governments in the world about their needs and how we can help them in bringing the quantum computing capabilities to all governments in the world. Here you can see how our 5-qubit quantum computer chip looks like. That's on the bottom left. And the 20-qubit chip is already produced. You can see there the package, and the 50-qubit quantum computer is already also in development phase. Here you can see the layouts, how the qubits are laid out on the chip. So the 5-qubit chip looks like an X. So it has a central qubit that is coupled to 4 surrounding qubits. The 20 qubit chip looks already more like a square lattice, and you can see that the 50 qubit chip starts to look more and more like a scalable lattice of qubits, where all the nearest neighbors are coupled to each other by very high fidelity couplers. Here I want to show you a little bit of our qubit performance. Here you can see a transmon Xmon qubit that is a single qubit in this case, where it has a readout resonator and a driveline. Of course, our qubits in the quantum processors are in a lattice and they're coupled, but here I just wanted to show you a picture of a single qubit and tell you that we can reach these 100 microsecond lifetimes for the excitations in the qubits, and also more than 100 microseconds of decoherence time, which means that if we do our quantum gates in tens of nanoseconds, we can have thousands of operations without errors for these single qubits. Of course, we want to extend these lifetimes, but currently, to the best of our understanding, the best lifetimes and decoherence times are in the hundreds of microseconds timescales in the world. We have done very high precision readout. In here, we demonstrate 99.3% readout fidelity, which means that if there's less than 1 error in 100 when we read out the qubits. So we can have 100 qubits on the chip, and measuring a few times, you would get the correct answer for all 100 qubits. The readout time is also very fast. Perhaps we can make it faster, and that is needed, of course, in the disruption phase. But maybe in a quantum advantage phase, we don't need to make it any faster. We actually want the readout fidelity to be just as good as possible. So here is some drawing of our 5-qubit quantum processor. You can see the qubits here and the readout resonators here. So the resonators are used to read out the qubits, and you can see that they are actually much bigger than the qubits themselves. And you have, of course, here also control lines. They're quite dim in this picture. They're coming to the qubits, which we are used to do this single qubit operations. In our own lab, for this 5-qubit chip, we have measured average single qubit gate fidelity of 99.9%. So there's going to be only 1 error in 1,000. For the 2-qubit gates, we have measured an average gate fidelity of more than 99%, which is very good. Of course, we want to improve this also to 3 nines and 4 nines in the future, but already the starting point here for the 5-qubit processor is very good. The readout fidelity in this processor, it's not 99% that I showed on the previous slide, because it's not optimized in this case for this particular chip, but we can, of course, achieve these very high readout fidelities in general. So here I have a little bit of an overview of what we can do with the 5-qubit chip in our own facility. I already talked about the gate fidelities, which are very important, and those gate fidelities then yield, for example, measures of concurrence, which means like how well we can entangle these different qubits on the chip. And this CHSH number that I have here, we just want to show it to show you that we can do with the quantum processor something that is non-classical. We can basically, if you noticed the Nobel Prize this year, it was given from these Bell inequalities, and this number tells us that we can break the classical limits of these Bell inequalities, and we can really do something that cannot be classically explained. And here's a little bit more data. For example, we have run some 5-qubit algorithms on the 5-qubit chip. For example, the Bernstein-Vazirani algorithm. When you run it, this would be the ideal solutions. Okay, actually no. This is what we get out from our QPU, and I think the ideal case would be probably just having 100% bar here, and you can see that it compares quite well with other vendors' chips. Here's a MaxCat problem, which is one of the very hard problems in computer science. Of course, for 5 qubits, it's not that hard to solve for a classical computer. But if you would extend that to 100 qubits, that would already start to be hard. However, we wanted to demonstrate that we can solve this MaxCat problem or use quantum computers to attack it with QAOA algorithm. And here you can see the simulation results of the ideal system, and here you can see our quantum computer results. So you can see clear correlation between what we would like to have coming out and what we have coming out. So the 5 qubits, we can work with them. But of course, like I said, that's not the end of the story. We are going for larger systems and for quantum advantage in near future. We did also publish and make an open source, basically an open source code that is published in GitHub of our quantum design platform. It's called, this design software is called KQ Circuits. We gave it to the community for free to use. You can design your own chips with this software just with a few lines of code. There are some libraries already published, and you can just say that, you know, I want my qubit 1 here, qubit 2 there, and the software will create you a chip design that you can then fabricate, or you can send to a foundry to fabricate for you. So in the future, we think this is very important because we're not the only ones who want to produce quantum chips. And when people have access to the software, they can easily design their chips. And perhaps in the future, we can also fabricate those chips in our foundry in Espoo and provide other companies also with the quantum chips for various purposes. One of the sort of focuses of our company is to design specifically chips or processors for certain applications. We think that in this term where we don't yet have the scalable sort of error-corrected quantum computer, if we do kind of squeeze everything out of the technology we have, may bring us faster to quantum advantage, useful quantum advantage. And for that reason, we have been already starting to kind of to tailor-make quantum chips for certain applications. Here is an example of NMR quantum chip. So we have published a paper this year, just last month, where we show theoretically a processor or a chip that could be used to speed up the calculation problems, the problems you have when you are trying to map out NMR data, trying to analyze NMR data. So those who are interested, I just urge you to go to look at this publication. We have, of course, it's not only theory, we have, of course, experiments going on, but this is what we have published so far about this use case. And we think that the transmon X1 qubit is great. It can do a lot of things, but at some point, it is very useful to have qubits that can do more accurate computations. Actually, already 4 years ago, when we were pitching our company to the very first investors and to the investors that did invest in our company, we were saying that we will build new qubits, we will invent new qubit types. And this is the Unimon qubit we have now come up with, which is quite simple in design, but yet we think it could bring better accuracies. So not only 99.9% probability of the gate, quantum gate to succeed, but maybe 4 nines, maybe 5 nines of gate fidelity. Here we can see some key characteristics of the Unimon qubit. It has higher nonlinearity or higher unharmonicity than the transmons, which means that we can do faster operations with it. You can see that the gate time, when we decrease it from 50 nanoseconds to 13 nanoseconds, the gate fidelity keeps on improving. So it goes to 99.9% and above in some cases. And we could still make it faster with this Unimon qubit. And that is, of course, one of our goals in the future, to show that the Unimon can perform more accurately than a transmon. One of the key features of the Unimon qubit is that it's fully insensitive to background offsets in electric field or charge. So it doesn't care about that at all. So if you basically put some strong electric field around your chip, or even actually in the chip itself, there are electrons that are hopping from one side to another. The Unimon does not respond to that background charge offset. That is very important because we know that in the chip, yes, there is a lot of charge clock noise, and in the transmon you have to make a compromise. You have to make a compromise that paying the price of decreased nonlinearity or unharmonicity, you will become more insensitive to this background charge fluctuations. In the Unimog, you don't have to make a compromise, which makes us happy and gives the possibility to optimize the qubit to perform better as a quantum in a quantum computer chip. Single qubit gates, the operations you do with single qubits is of course not enough. You need to be able to do very high precision 2-qubit gates, and we're happy to show you that in this so far paper that is only in archive, but we have submitted it to a scientific journal for peer review. We have been able to show that we can make very high fidelity 2-qubit gates, 99.8% fidelity, which means that maybe only on average 2 failures in 1,000 trials. That is encouraging. That's on the level of the best 2-qubit gate fidelities that anybody has achieved in the world for these qubits, superconducting qubits. So we know how to do them well, and we want to put also this new type of 2-qubit gates into the larger chips that we are making. We think that, raising the number of qubits is great. You can show that you can put more and more on the chip, but if you don't have good fidelity, you cannot really use the qubits in your computations. Like if you have 100 qubits, but if your 2-qubit gate fidelity is only 99%, okay, you can do a single, or let's say 2-qubit gate sort of operations for all qubits, and then your algorithm is going to fail about half the time. So you really need that fidelity to be able to run, reasonable depth algorithms with these present-day quantum computers before we have quantum error correction. Of course, with quantum error correction, then you can use more and more of the qubit numbers to make higher fidelity operations. But now, before we have that, we have to be constantly improving the gate fidelities. Here is a little sort of glimpse of how our coupler works. So you can see that there is qubit 1 and qubit 2, and between those we have designed a circuit with optimal parameters or optimized parameters to yield these very high gate fidelities. We think this design is going to take us to the quantum advantage. And well, basically I already said this. The fidelities are already state of the art, and we are doing our best to put this technology into the larger chips. So thanks for your attention. And well, I don't know if there is any questions, I'm happy to answer. I don't know if there is time for those. So.
But of course, there is time for one question. Please, is there a question? Is there anyone capable of presenting a question? Please.
You're talking about fidelity on 1 and 2 qubit gates.
Just a second, you will get the mic.
Right. So also those people who are okay, thanks. Antti Nalman. A quick question. You're talking about the fidelities of 1 and 2 qubit systems, which obviously takes us very far away. Just out of curiosity, have you been toying around with 3-qubit like Toffoli gates and such, or is that even possible in a conducting like superconducting qubits?
Yeah, so you can with 1 and 2 qubit gates, you can build any quantum gate for n qubits. That is some work I did 20 years ago, how to, split up an arbitrary n qubit gate into 1 and 2 qubit gates. So that is why we are typically plotting the fidelities for 1 and 2 qubit gates, because the larger gates will follow. And on the slide about the Bernstein-Vazirani algorithm, for example, or the MaxCat for QAOA algorithm, effectively you are doing 5 qubit gates. So you could see the data on that slide.